Hello again. This is CS 480/6/680 Introduction to Machine Learning as taught at the University of Waterloo in fall 2024. This is lecture 18, and today we're going to be talking about variational autoencoders as well as normalizing flows. So this is going to be the first part in a two-part exploration into what are known as deep generative models. So what is a deep generative model, and why explore these now at this point in the course? I would expect that a lot of you, if you're enrolled in this course, potentially you've been keeping up with the cutting edge techniques in this field. You might already be familiar with this term, and perhaps you've been excited to get to these topics at the frontier of machine learning methods for, potentially for quite some time. But yeah, for most of this course, we've been spending a lot of our time thinking about what can really be collectively called discriminative models. And so in a discriminative model, the goal is to learn a predictor given a set of observations. So yeah, in this setting, we're given a training data set, and we want to learn some function f that's going to take some input x and output some y that's close to the true output as we saw in our training data set. Of course, we're interested in learning a mapping from the input to the output, such that we can generalize to inputs that we haven't seen before, inputs that weren't in our training data set. But yeah, most of our lectures have really been focused on this. So for example, the perceptron, support vector machines, decision trees, the multi-layer perceptron, as well as convolutional neural networks. They've really been emphasizing this mapping between an input to an output. Where our focus has been on learning a decision boundary in the case of classifiers, or learning even learning continuous valued predictor with regression models. We have also encountered a totally different goal in generative models. And so here we weren't interested in learning a mapping between an input and an output directly. Instead, we wanted to be able to say something about the process that generated the observations to begin with. So yeah, we wanted to understand or be able to describe that process in some way. And specifically, we wanted to approximate probability distributions such that we could generate new samples. So we wanted to define a probability distribution over a random variable x such that we could draw new samples from it. So examples of this were the kernel density estimator, as we saw it, and then the Gaussian mixture model that we tackled with the expectation maximization algorithm. Yeah, quick recap of generative models so far. We started off with really simple examples of fitting a simple univariate Gaussian to a set of observations. So we tackled that with maximum likelihood estimation to define the joint density over a set of observations, xi. We also expanded on this by using maximum a posteriori estimation to incorporate prior knowledge of a distribution over observations in order to anchor the subsequent distribution that we learned to some prior belief. Yeah, encountered a few applications of this, Bernoulli distribution, as well as Gaussian, the Gaussian. And then more recently, we looked at Gaussian mixture models, Gaussian mixture models for multimodal data where a distribution could have multiple peaks and be well described by a mixture of Gaussians with different mixing weights and different means and variances on each of the modes. And we tackled that with expectation maximization algorithm, incorporating which allowed us to incorporate or which involved incorporating a set of hidden variables or an auxiliary distributions over those hidden variables Qn of z. So those techniques were great and they got us pretty far, but real world data often can't be modeled quite so simply. So for example, the MNIST data set, which is this set of images of handwritten digits. So each of these images is a 28 by 28 array of pixels. So in total, we've got 784 pixels. So in order to characterize the distribution over these images, we'd be dealing with a 784 dimensional space. And then within each of those features, we'd be looking at each of those features would describe the grayscale intensity of a single pixel. And so within that 784 dimensional space, I can't picture that. I'm sure that even my intuitions would lead me astray in order to even describe what that would look like. But we might expect clusters of points somewhere corresponding to a zero, and potentially something like a one, and maybe the clusters corresponding to a one and a seven might overlap a little bit, because sometimes a one can look like a seven. But yeah, it's not clear what that would even look like, what a distribution would look like. And in that case, because we cannot define a distribution, where we'd be hard pressed to come up with how to parameterize that in order to fit the parameters and learn what and to be able to draw new samples from it. So if we wanted to have some new images of a 3 generated, for example, where would we need to start in that high dimensional space in order to draw something new from it? Would it still look like a 3? How far away from an average 3 would we need to could we get in order to draw something meaningful? Is an average 3 even a reasonable question to ask? So yeah, there's difficulties in trying to pin down exactly what a distribution should look like when we're getting to this point. We don't know what those parameters should be. So the MNIST data set is a very popular, well-studied example in the field. Another benchmark is the fashion MNIST data set, which is surprisingly exactly how it sounds. So it's this array of images of clothing and accessories. So what would it mean to be able to generate some new clothing or accessories from this data set? How can we parameterize over such a data set of images in order to be able to draw meaningful samples from it? All we've had so far is the simple parameterized distributions of dealing with Gaussians and the Bernoulli model. The closest tool we encountered to be able to deal with a situation like this was kernel density estimation, which allowed us to focus on building a distribution from the data itself to build up an empirical distribution. There are some drawbacks to applying KDE in high dimensions that that I won't get into, but suffice to say, it doesn't KDE doesn't do very well in high dimensions. So uh, so yeah, in real world data is it's hard to describe the probability distributions in that space, but there's no what I'd like to suggest is it's still we still need to be able to talk about these data sets and talk about these types of data from a probabilistic perspective. Um, and so to give you an example, um, a lot of the the generative tasks that potentially you've seen or encountered um, within the last few years, they rely on probabilistic concepts. So, for example, take an image generation task. So, if you played around with the Dolly here, yeah, potentially, uh, yeah, what you would do is you would write in some text about what you would want the model to generate. So for example, give me a teddy bear that's swimming at the Olympics 400-meter butterfly event. So you would provide this text prompt, and it would generate this image. And so what's happening here is it's conditioning the probability distribution over X on a particular condition C. And in this particular case, you're providing a text prompt, and it's giving out an image. So it's first conditioning all the possible images that it could generate on that text prompt C, and then it's giving you a particular sample from that starting point at the risk of some loss of precision. It's kind of starting from that point. Yeah, so some other examples, cute corgi lives in a house made out of sushi. That's what it came up with, and sloth holding a small treasure chest. Uh, yeah, so the some other examples are like image captioning. So there you want the caption to be some text. So you want the model to generate a caption, but it needs to be meaningful. It needs to be relevant to a particular image. And so you can't just have it generate anything at all. You want it to generate something that's custom to that image. So in that case, you condition the distribution over possible outputs on that image, and then it's going to spit out some text. And so in that case, yeah, we an application of that was with convolutional neural networks, where yeah, it could discern some meaningful vector from an image, and use that as the condition for the caption for the text output. Another example was when you provide some prompt, and then it's going to continue. A last example is when yeah, the condition itself is an image, and the desired output is an image. So we want to draw a sample from a distribution over images, and condition that distribution on a particular image. And so yeah, why would we want to do that? A couple applications are things like in painting. So in this row of images here at the bottom, this is the original image, and parts of it have been occluded, so blanked out by these white bars here. And so the task of the model then, of the generative model, is to predict or estimate what and to fill in for these occluded areas. So the output of the model is in this middle row here. And it's yeah, it's successfully inferred the missing parts of this boy's face. Didn't know that there was didn't anticipate that there would be a pole there. Um, or another one right here. But did a pretty good job of filling in for the trees, as well as the face, um, inferring some people in the background here. So that's so pretty neat there. I guess the little boy had a chunk missing out of his hip, but uh, yeah, otherwise pretty cool job. Um, some other applications are things like maybe part of the image is cropped, and the model needs to predict what should have been in the cropped area. Things like colorization. So you provide it a black and white image, and it's going to try to figure out what the colors should have been. So you condition the distribution on an image, and then it's going to generate an image. Um, Another example might be, a corrupted image, something that's been noise corrupted, and it's going to clean it back up for you. Okay, so yeah, how can we leverage these probabilistic frameworks while allowing and enabling us to fit realistic distributions? So the types of distributions that we're likely to see in real world data. And so the approach that we're going to be focusing on for the next two lectures is going to concern architectures that are collectively known as deep generative models. And the idea here is that we're going to use deep neural networks to learn a complex mapping from a single latent vector to the observed data. And the idea is that we're going to use deep generative models to approximate this probability distribution for us. So use a very high dimensional parameterized representation of the probability distribution, such that we can generate new samples from that distribution. There's many different types of deep generative models, and so we're going to be focusing on four. So specifically, we're going to be looking at the variational autoencoder, or VAE. Then we're going to be turning our attention to flow-based models, and then so these we'll be talking about today. And then in the next lecture, we're going to be turning our attention to generative adversarial networks as well as diffusion models. All right, so onward to VAEs and flow-based models. Yeah, and yeah, we'll be doing that next week, or next lecture. All right, so yeah, onward to variational autoencoders. Okay, so we're going to begin our discussion of deep generative models with variational autoencoders, or VAEs. These models are actually based on an earlier model called an autoencoder that dates back to the 1980s. So before we get into VAEs, let's just examine the autoencoder and what it achieves. So an autoencoder is a feed-forward architecture trained to approximate the identity function in an unsupervised manner. And so we can think of it in three key parts. So there's the encoder G and a decoder F, and then a latent state Z, which is usually lower dimensional than that of the data. And so the job of the encoder is to map some high dimensional input X into the lower dimensional representation Z. And then from there, the decoder maps that representation back to data space. And the specific goal is to try to reproduce an output X prime that closely resembles the original input X. So for example, if we presented a 4, an image of the digit 4, we would want this architecture to output an image that we could also readily recognize as a 4. And so of course, if G and F were such that the encoder perfectly replicated the input, this model would be trivial and useless. And so instead, this latent state Z is usually selected to be lower dimensional than that of the input to introduce an information bottleneck in the architecture. And so this means that the encoder is in some ways forced to learn only the essential features of the data in order to reconstruct the output. And so because of this, the purpose of an autoencoder goes beyond just copying input to output. An autoencoder is useful in at least a couple ways. So first, they compress data into a smaller, more efficient representation, for potentially for compact storage. And then second, because autoencoders can reveal interesting and meaningful representations of data in the bottleneck layer, that capture the essential features of the data set. These learned representations can be useful for downstream tasks like clustering or anomaly detection or some other task. Autoencoders can serve as either a practical tool for compression as well as a conceptual tool for understanding the structure of more complicated data sets. And so in practice, the encoding and decoding functions are approximated using neural networks. In the simplest possible case, we could have a single hidden layer. So our d-dimensional input vector x is compressed into a latent representation z through the encoder weights wf, and then expanded back to x prime using decoder weights wg. And so for the network to behave like an autoencoder, we want to select those weights such that the reconstructed output x prime is a close match to the original input, subject to, of course, the constraint on the lower dimensional representation in that bottleneck layer. Specifically, these weights are optimized to minimize what is known as the reconstruction loss, which measures the difference between the input x and its reconstruction x prime. So for a simple linear autoencoder, the loss function penalizes deviations between the input and its reconstruction as the squared difference between the original and the reconstructed inputs. Most often, we're interested in hidden units with nonlinearity, which allow the network to model more complex relationships in the data. And then the reconstruction is based on the activations activations of neurons in that hidden layer. So some activation function H. And then there's a few variations on these basic ones, these basic linear, nonlinear autoencoders. Sparse autoencoders introduce an L1 penalty norm on the activities alongside the reconstruction error with a hyperparameter lambda, which encourages only a small subset of the neurons to be activated at once. And then denoising autoencoders refer to a training paradigm, actually, where the network is trained to reconstruct the original input from a corrupted version of it, x tilde. So for example, if we had a noisy image of a digit 4, the network should learn to restore it to a clean form. And so this approach enhances robustness by forcing the network to learn the relationships between dimensions of the input data. But yeah, regardless of the specific objective, the goal of these autoencoders is to compress data into a meaningful representation in the bottleneck layer and to ensure that the reconstructed output closely resembles the original input. So for the rest of this talk, I'm going to use a block diagram architecture for the autoencoder in place of a neural network. Also, while I've kept things simple in the discussion so far and focused on a single hidden layer encoder and decoder, each of these could have multiple layers in general. You could also impose structure, like using weight sharing to have a convolutional neural network encoder. The training objective of reconstruction loss still applies. We want to optimize the weights would be we would be optimizing the weights just over a more complicated network. A fundamental limitation of an autoencoder, though, especially when it comes to generative tasks, is in the nature of the latent space that it learns. So if we train an autoencoder on say, the MNIST handwritten digits task, you can visualize the mappings of respective points in the data set in the lower dimensional space. So in this plot here on the right, we're looking at a 2D latent space, a 2D latent space of an autoencoder corresponding to MNIST samples. And what we can see are distinct clusters corresponding to each digit. And so this structured clustering it's good for reconstruction because it simplifies the decoder's task. Each cluster corresponds to um, a specific input class, like a particular digit, for example, 7 and 1, 3's down here. But in order to generate new images, the model needs to, by definition, sample from regions of the latent space that was not in the training data. And so this is, because the purpose of a generative model is to create novel outputs, which requires, exploring parts of the latent space beyond the specific encoded representations that it was trained on. And so why this is a problem is because this clustering, we see that there are gaps and discontinuities in the latent space. And this is a significant challenge for generation tasks. For example, if you were to draw a latent vector in between this 7 and 1, the decoder is unlikely to produce a meaningful output because it was never trained to decode. It was never trained to decode a point in this area in the latent space. The decoder was never optimized for this part of the latent space. It never saw something like this during training. And so it doesn't know how to handle a point in that space. And so what this means is that while an autoencoder is great for reconstructing or compressing existing data, it's not so great for generating new realistic samples or exploring the underlying distribution of the data set. And it's also not clear what scales we should even select to define a distribution over the latent space. So for example, in this plot, one latent dimension, this first one, it varies almost twice as much as the other one. And so, and that kind of information that's not available to us a priori. The only way to find that out is to actually go and inspect the latent embeddings directly, as we have done here. So it's possible to somehow avoid creating those gaps, as well as control the scale of embeddings in the autoencoder's latent space that make it so hard to generate new samples. And so this is where variational autoencoders or VAEs come into play. And so unlike standard autoencoders, which compress input data into a latent space representation that might have those disconnected regions, VAEs are designed to ensure that the latent space is smooth and continuous. And so the idea is that with that smooth and continuous structure, you can generate meaningful samples by interpolating between points while sampling randomly from the latent space. So yeah, what do I mean by this? These two plots here, really get at the difference in the structure of the latent spaces between these two models. So on the left, this is the latent space of the regular autoencoder that we just saw. It has those clusters of points that are scattered and disconnected, big gaps between them. And then on the right, this is the latent space of a VAE. And so what we can immediately see is that the clusters are a little bit more continuous. And the scales of the two embedding dimensions are actually roughly the same. And so this smooth structure is going to allow us to move through the latent space in a way that produces coherent and realistic samples because the decoder is more likely to have seen everything in this region. So yeah, for example, the transition between a 0 and a 6 in this plot here, this would generate outputs that should roughly gradually blend from one to the other. But yeah, how exactly do variational autoencoders, VAEs, how do they achieve that kind of structure in their latent space? And so they solve this issue of an unstructured latent space by doing something that's a bit surprising. Specifically, they introduce a probabilistic approach to both encoding and decoding. Um, and so what this means is that instead of mapping inputs to fixed points in the latent space, as with standard autoencoders, VAEs map inputs to probability distributions. Specifically, for each input X, the encoder maps these to parameters of a distribution in the latent space. Typically, and for today, an isotropic Gaussian is chosen. So the encoder maps the input to a mean vector and a diagonal covariance matrix. And then a latent vector Z is sampled from this distribution to given the parameters. And then the decoder maps that latent vector back to the data space to produce a new sample, X tilde. And so this sampling from a distribution during training means that during training the decoder is exposed to a range of variations around each encoded point. And so this is going to help ensure that the latent space is both continuous and smooth to allow the decoder to generalize effectively. VAEs go a step further and specify a prior distribution, P of Z, over the latent space, which defines how latent variable Z should behave globally across all inputs. So this prior is a fixed distribution defined over the latent space, and it's usually selected and for today as an isotropic multivariate Gaussian distribution centered at the origin. So this prior is going to act as a form of regularization and enforce global structure on the latent space beyond the local smoothness granted by the sampling procedure itself. And then during training, the encoder is going to learn to approximate the posterior distribution of latent variables given the input X. So Q of Z of X parameterized by phi. And so it's this learn posterior that should align closely with the prior if we select the training procedure correctly. And then the decoder learns the likelihood of the data given the latent variable Z. So P of X given Z parameterized by theta. So yeah, taken together, this probabilistic representation is going to allow the latent space to be continuous and smooth, making it much more suited for generating new points. Right, posterior distribution over latent variables given the input, and then the likelihood of the observed data given the latent variable. And this architecture builds on a traditional autoencoder. So there's still an input, a latent, and an output, but now we've added probabilistic elements. So the structure just we're sampling meaningful variations of an input and potentially even interpolate between different points in the latent space. So to illustrate what a VAE does, we can we're going to be focusing on that simple case of a VAE based on Gaussians. And so what this means is that both the encoder and the decoder are designed with probabilistic assumptions about their outputs. So yeah, on the left, the input data uh, with dimension up to XD is passed the encoder network. And then instead of mapping each input to that single deterministic point in the latent space, the encoder produces two outputs for each dimension of the latent variable. So we've got a mean mu and a standard deviation or variance sigma. And so I've assumed a two-dimensional latent space. But yeah, if we have m dimensional latent space, then we would need a mean and a variance for each dimension in the latent space. And so these values, they parameterize a Gaussian distribution. So the encoding's not a fixed point, but they're parameters of a probability distribution. And then a key aspect of VAEs is that once we have this distribution, we then draw a sample from it. And so there's a stochastic sampling step. And so this ensures that the latent space, it essentially fills in the gaps in the latent space to allow for that crucial ability to interpolate between training points. And then the decoder network takes that sampled latent vector and maps it back to data space, x tilde. So we're attempting to reconstruct the input data x from that latent variable. And so during training, the model is going to learn to minimize the reconstruction loss, which measures how closely the reconstructed data matches the original input. And so this combination of probabilistic encoder and decoder allows the VAEs to achieve two goals simultaneously. So they're generating a smooth latent space and enabling the generation of new data samples. And so a VAE is a probabilistic generative model designed to define a joint distribution between a latent variable z and the observed data x. And by definition, this joint distribution can be broken into two parts. So there's the prior distribution over z, and this is going to this tells the model how z is expected to behave, and the likelihood of observed data x given z, which describes how the data is generated from the latent variables. So it's this prior z that is usually set to be a standard normal Gaussian distribution with zero mean and isotropic unit variance. So the true posterior distribution, which would represent the probability of the latent variable z given the observed data, that's what we would ideally use to infer z from x. But computing that true posterior distribution is intractable because it would require evaluating the marginal likelihood of the data, and that would involve integrating overall possible values of z, which could become computationally prohibitive, especially in high-dimensional latent spaces. And so to solve that, to get around that problem, VAEs work off of an approximate posterior distribution. So Q of z given x parameterized by phi. And this is called the recognition model. And so this approximation, we're parameterizing by phi, which are the parameters of the encoder neural network. And so the role of this recognition model is to provide a tractable approximation to the true posterior. And yeah, as we'll see next, during training, the VAE is going to optimize both the encoder parameters and the decoder parameters to make the approximate posterior as close as possible to the true posterior. But yeah, so what should we optimize exactly? Um, and so before presenting the math, we can just first think about this in terms of the structure of the latent space. And let's keep that MNIST data set in our heads. So on the one hand, we want samples from the latent space where the encoded inputs are mapped to look like the prior that we defined. So in this case, we want that smooth, well-structured Gaussian centered at the origin, but we would want some characteristics of the input data distribution to be preserved in samples from the latent space. So we would want to see similar samples in the latent space correspond to the similar samples when mapped back to the data space, and conversely for points that are dissimilar to be far apart. But if we let the encoder focus only on making the posterior distribution look like that prior, it would learn an identical distribution for every single input point. And this would result in samples that are, totally disorganized, just scatter them across the space in ways that don't preserve any relationship between similar inputs. And so this would make it hard for the decoder to learn these latent encodings to generate meaningful outputs. And so what we need is a way to walk that fine line between matching the prior and preserving semantic similarity in the latent space. And so the VAE objective is going to strike a balance between regularization and reconstruction. And by regularization, we mean that we want to ensure that the posterior distribution over the latent variable, given an input, matches the prior distribution. And so we use KL divergence to quantify some notion of how far the encoder's output distribution, Q of Z given X, over latent variables Z given a set of inputs X, deviates from the prior that we specified. And as I mentioned a few times, we take this prior as a standard Gaussian distribution. A standard Gaussian distribution denoted as a scripted N, so mean of 0, and isotropic unit covariance matrix. So that's the identity matrix. So it's isotropic unit variance. And then minimizing this KL divergence is going to encourage the inputs to be mapped smoothly over the latent space and aligned with the Gaussian prior. And so without that term, the latent space would have those gaps and discontinuities that we saw with the deterministic autoencoder, which would lead to the poor generalization when trying to generate new points. And then the second objective is reconstruction, and this encourages the decoder to accurately reconstruct the input data from the latent representation Z. And so mathematically, this is expressed as maximizing the expected log likelihood, where P sub theta of X given Z, that represents the decoder's likelihood of reconstructing X given the latent variable Z. And so this term ensures that the latent representations retains the meaningful information about the data, allowing the decoder to produce high quality reconstructions. So we can put these two objectives together, and it can be shown. Unfortunately, we won't have time for this, but that these two objectives can be combined to form a lower bound on the log evidence, P sub theta of X. And so this is the marginal likelihood of the data under the model. And so as KL divergence is non-negative, the log evidence can be improved by minimizing it. And so to make the posterior distribution over the latent variables match the prior, and thereby maximizing the evidence. And so this On this right-hand side, this is the evidence lower bound, and log of p sub theta of x, that's bounded from below by the sum of the reconstruction error and the negative of the KL divergence. But how can we train this network, given the fact that VAEs are fundamentally stochastic? How can we back propagate the gradients? We've got this latent variable z that's sampled from a probability distribution, and this stochastic nature of this sampling is to prevent the gradients of the loss function from flowing back to the encoder parameters that we need. And so to get around this, we use a pretty clever workaround called the reparameterization trick. And the idea here is to move the randomness out of the latent variable z and into a separate noise variable epsilon, which follows a standard Gaussian distribution. And so we redefine z as a deterministic transformation of mu, sigma, and epsilon. And so instead of directly sampling z from the fitted posterior distribution over the latent space given the input, we now sample epsilon from a noise distribution and then compute z deterministically. And so this reformulation allows us to express z in a way that preserves the stochastic behavior that we need while enabling the gradients to flow through z for back propagation. When using generative models, you could simply want to generate a random new output that looks similar to the training data. And you can certainly do that with VOEs. But more often, you might like to alter or explore variations on the data that you already have. And not just in a random way either, but potentially in a desired specific direction. And so this is where VAEs work better than many other methods currently available. So this image here, this illustrates interpolation with a VAE trained on the MNIST data set. And so interpolation is performed by selecting 2 points in the learned latent space corresponding to 2 different digits, and then linearly blending between them. And then as you move along the latent space between these 2 points, the VAE decodes intermediate points into meaningful, smooth transitions between the digits. So for example, you start with a point corresponding to a 7 and then interpolate towards a 1. And so what we can see is that the generated images, they morph pretty seamlessly between the 2-digit classes. And so we've passed through some intermediate forms that still resemble valid digits. And so what makes this possible is the structured and smooth latent space that the VAE learns. So because the latent space is regularized to follow a Gaussian distribution, each point corresponds to a plausible representation of the data. And so this property allows for controlled transformations like the interpolation here, like the interpolation that we saw here. And this makes VAEs pretty powerful tools for tasks where we might like to explore the data and manipulate it in some way. So what benefit did we gain by encouraging more continuity in the latent space for variational autoencoders over the deterministic autoencoders that we started with? And so the most important advantage is that VAEs define a proper generative models. They can generate entirely new, sensible samples by decoding latent variables sampled from the prior distribution. So this is fundamentally different from the deterministic autoencoders, which can only reconstruct images based on the specific latent codes that were derived from the training data. And so what we can see is that so an example of an AE versus VAE. These are training images corresponding to a set of celebrity faces, the Celebre data set. Um, and then in the deterministic autoencoder, to try to generate new samples, we're going to pick a random spot in its latent space, a random latent vector, and then try to decode it. And so what we can see is that the images that were generated are pretty meaningless. None of these images look like faces. And this is because the latent vectors that we have chose, they probably live in those gaps in between examples that the decoder has seen. And so the decoder doesn't know how to do that. It doesn't know how to map between them. The VAE samples, on the other hand, um, the decoder has more likely seen the samples that we've drawn from it. And so when we can generate plausible faces, these look like faces. These images look like faces. And so what we can see is that the VAEs definitely improve. Images are still pretty blurry. One, this happens because the VAEs don't optimize the exact log likelihood of the training data. Instead, they're optimizing a lower bound on it. Additionally, because of how VAEs model data distributions, the decoder often is modeling pixel values as independent Gaussians, and this can lead to averaging effects in the generated samples. So there's VAEs are still they're generating somewhat blurry samples. Okay, so we just saw that VAEs can be used to generate meaningful novel outputs by mapping inputs to a probability distribution over the latent space. And on the image generation task that we saw, the outputs definitely improved over that that of the deterministic autoencoder, but they weren't quite as sharp as we would expect to see for images. And the one problem there is that we were trying to align the input embeddings to a simple Gaussian distribution. And so this begs the question, are there generative models that can define more complex distributions? And one such model is the next kind of deep generative model that we're going to talk about, which are those based on normalizing flows. And so these are going to retain the probabilistic approach that the VAEs had, but allow for a more expressive latent space to be able to, and also to enable computation of exact log likelihoods. And so normalizing flows can complement VAEs, but they're also quite useful on their own. The key idea behind normalizing flows is that they provide a way to transform a simple distribution like a Gaussian into a complex one by applying an invertible transformation or a series of invertible transformations. So yeah, we might start with a simple probability distribution like a multivariate Gaussian, and then by applying an invertible transformation, we can work this into a much more flexible and an expressive distribution that might be more representative of the real world data real world data sets that we might be dealing with. And so yeah, with these transformations, normalizing flows can allow us to represent very intricate data distributions, but starting from something that is mathematically quite simple. And so the core advantage that we're going to see of normalizing flows is that these transformations are designed to preserve the ability to compute exact probabilities. And so in contrast to models like VAEs, where we only optimized a lower bound, with normalizing flows, we're going to explicitly represent and compute the density of the transform distribution. And so this is particularly useful if we need a precise representation of the data. With neural networks, then these transformations are learned such that they map the source distribution like the Gaussian on the left to something to a complex target distribution that resembles the underlying structure of the data. So how is it that normalizing flows can transform a simple distribution into a more complex one? So these models exploit the fundamental principle of conservation of probability mass, which ensures that any transformation of a random variable preserves the total probability. And so to see how that works, suppose that we start with a random variable that is sampled from a uniform distribution on the interval of 0 and 1. And then by applying a transformation f to x, we can obtain a new variable y, which is 2x plus 1. And so this new random variable is going to span from 1 to 3. So we started from a distribution over uniform interval 0 to 1, and then we're mapping to a uniform distribution of that spans 1 to 3 to get y. And so what we can see is that the distribution is now non-zero over a greater range. But in order for this to be a true probability density function, in order for P of y to be a true probability density function, the total probability must be the same. And specifically, it must be 1. And so to preserve the total probability mass, we have to scale the density function accordingly. And so in this example, because the domain is scaled by a factor of 2, from a unit interval to one of length 2, the density must decrease proportionally. So we want to have this from 1 to 0.5. And so we can formalize this relationship with derivatives, differentials. And so because we know that the probability over y must equal to that over x, and both of those must equal to 1, we know that the probability density at y is equal to the density at x times the absolute value of the rate of x with respect to y, the rate of change of x with respect to y. Okay, so let's now consider transformations over multivariate distributions. So yeah, let's start off with a source distribution, which is a uniform distribution of a square. So there's non-zero probability mass in the green region, and then zero outside of it, everywhere else. So we can imagine some transformations that we might apply to this distribution. A trivial one would be if we were to shift just simply shift this. In such a case, we haven't affected the rate at which the distribution, or we haven't changed the rate at which our source variable x is changing relative to the target variable y. So we wouldn't need to adjust the probability distribution in this case. Suppose instead that we started with a unit square with one corner anchored to the origin. And so it was defined by points 0, 0, 0, 1, 1, 0, and 1, 1. And if we were to apply a linear transformation, defined by some matrix T with arbitrary elements A, B, C, and D, and then transform, apply that to the original points x, then our variable y would be defined by 0, 0. So and then the point 0, 1 would get mapped to AB. The point 1, 0 would get mapped to CD. And then the point 1, 1 would get mapped to A plus C and B plus D. And then in general, the square that's anchored at the with one point anchored at the origin, that's going to get mapped. It's going to get stretched and skewed to map into what is generally a parallelogram. The total area of which is AD minus BC, and so this is actually the determinant of this transformation matrix T. This determinant, or more precisely, its absolute value, that tells us how much the linear transformation scales. So the total area of that parallelogram is the absolute value of the determinant of the transformation matrix. And that determinant, the absolute value of the determinant, that tells us how much the linear transformation defined by T scales the area or volume in higher dimensions. So for example, if this determinant of t were greater than one, then the area would be increasing. And if it's less than one, then the area is going to decrease. And we can generalize this concept straightforwardly to higher dimensions. And so it's this property of determinants is fundamental to understanding how linear transformations affect probability densities, because it directly scales the density to preserve the total probability mass. Okay, so that was linear transformations. But for the kinds of generative tasks we'd like to perform, we're most often interested in nonlinear transformations. So yeah, we might start with a uniform distribution over some square region as the source. And then we're interested in obtaining a uniform distribution, potentially over a circular region instead. And so in order to make this kind of transformation, we would actually need to distort the space differently at every point. And so we can do this with, some properly defined nonlinear function. But this would make it harder to adjust probabilities while preserving the total probability mass, because it's not, we're not just applying a linear transformation. We're not just stretching and skewing this into a parallelogram anymore. And so, yeah, while it's true that the transformation has an overall nonlinear effect on the distribution, we do know that if we were to zoom in on a patch that's small enough within this distribution, we could observe, locally linear behavior in that neighborhood. So specifically, if we were to zoom in on a small patch of this circle, an infinitesimally small patch, then we would be able to describe the resulting transformation around that point as a locally linear transformation to transform a small patch of that surface into a parallelogram. And so we can characterize this local linearity using the Jacobian matrix, which is a multidimensional generalization of the first derivative. And so it's going to contain all first order partial derivatives of the transformation function f in question. Yeah, so crucially, the determinant of this Jacobian matrix in general is the rate of volume change at any point. So a powerful consequence is that we can compute the probability density of the transformed variable using its relationship to the source variable. And so to see how, let's define P sub u of u as the distribution over the source variable. And then P sub x of x, let's let that be the distribution over the target variable. Then let's let f be some invertible function such that f of u gives us x, and then we can recover u from f inverse of x. And so as before, we know that the total probability mass has to be preserved. And so the integral over both distributions over their respective domains, they must evaluate to 1 in order to count as a true probability distribution. To preserve probability mass, therefore, we multiply by the reciprocal of the determinant of the Jacobian of f evaluated at u. And then to compute the exact density P sub x of x, we can exploit the fact that f, as we defined it, is invertible, and apply f inverse to obtain u, f inverse to x to obtain u, and then evaluate the density under the source distribution. Evaluate the density under the source distribution, and then scale by the determinant of f inverse. And then you can, what's powerful is that we usually select the source distribution P sub u to be easy to evaluate, like a standard normal distribution. So that's handy. But how can this ability to transform probability distributions help us with generative models? And so in generative models, we're often concerned with estimating the probability density function P sub x of x which describes the underlying distribution of the observed data. And we know that this is hard for real world data, which often follows those complex or intricate distributions for which we, can't easily fit a distribution using simple functions like a Gaussian. And so we can bring in normalizing flows to help here to allow us to transform a simple, well understood base distribution like a Gaussian into a more complex distribution that better approximates the data. And then for such a model, we would be interested in the likelihood function, the product of probabilities for each observed data point in the data set. And then we can, re-express that in terms of the simple base distribution, P sub u of u, and the determinant of the Jacobian matrix of the invertible transformation F. That as we said before, maps maps from the base distribution U to the data space X. The optimization objective then is to find the transformation F that maximizes the likelihood of the observed data. And as as before, when we've applied MLE in the past, we don't usually directly maximize this product of probabilities. Instead, work with the log likelihood. And in this case, it reformulates the training objective, the problem into two terms. One for the log probability of the base distribution, and then another for the log of the log of the determinant of the Jacobian. So how nuanced and flexible of a distribution can we actually model using a single function? And so it turns out that a single invertible transformation can be used to approximate any smooth distribution. In some cases, it might be convenient to define a series of simple but invertible transformations known as bijectors to map a simple base distribution into an intricate target distribution. And so the key idea here is that each transformation F sub I is, that's a smooth invertible function or invertible transformation. And because a composition of invertible functions is also invertible, this means that we can compute the density at each intermediate step in the chain using the base density P sub 0 and the Jacobian of the respective transformations. And then in practice, each bijector is implemented in a neural network like architecture, with learned parameters to maximize the likelihood of the data. One thing to keep in mind, though, is that these architectures have to be carefully designed in such a way to permit only meaningful and tractable transformations. Specifically, the parameterization needs to ensure that these transformations are invertible and also allows for efficient computation of the Jacobian determinant. And that last consideration is pretty crucial because computing the determinant of a general Jacobian can be computationally expensive, especially as we go into higher dimensional spaces. All right, that brings us to the end of this lecture. Quick recap before we close out here for the day. So what do? We considered today two deep generative models that allow us to have an explicit representation of a distribution. So that was variational autoencoders as well as normalizing flows. We also saw started off our discussion of variational autoencoders, VAEs, talking about autoencoders, and we saw that those two are quite different, both in terms of the structure of their latent spaces as well as the stochasticity of their outputs. We did spend quite a bit of time talking about how exactly VAEs generate new samples, or how the decoder generates samples by drawing some random latent vector and then mapping it back to data space. We talked about the loss function of the VAE, how it balances regularization and reconstruction error. Talked about the terms in it using the KL divergence, using the KL divergence to minimize the distance between the posterior distribution of the latent variable given an input and the prior distribution. I also talked about why a Gaussian prior makes sense as a way to impose structure on a VAE's latent space, and the reparameterization trick in order to actually do backprop and train up this network. Did talk about a couple limitations of a VAE, illustrated that with the image generation task that we saw. And also how we can use VAEs to explore variations on existing data, specifically interpolating between points in the latent space. And then getting close, moving on to normalizing flows. Normalizing flows allow us are a bit different from VAEs in that they allow us to have an explicit density evaluation of the data distribution. And then we also saw how we can use invertible transformations to compute probability density of the target distribution from a source distribution as well as the Jacobian determinant. All right, thanks for your attention. Hope you learned something today. We'll see you back here again next time for when we'll move on to talking about the second part of deep generative models, where we'll be moving into generative adversarial networks as well as diffusion models.